All right, guys, we're going to be starting a new unit today, Unit 2, Section 2.1, Day 1, Inductive Reasoning. So the first word we need to look at is conjecture. Conjecture is an unproven statement that is based on observations. An unproven statement based on observations. So that could be even, the world we're in now with all the COVID-19 predictions. Back at the very beginning, they could say, hey, we believe COVID-19 is this deadly of a virus based on what we've seen in this first outbreak. That would be conjecture. It's unproven, but based on observations. That is conjecture. And we'll be using it in math, obviously. Give you some room to write that. All right, inductive reasoning is making conjectures based on patterns. So take that same COVID situation at the very beginning. Once we see other situations or other cities or areas with COVID outbreaks and the patterns that start to develop, we can make better predictions. And that is called inductive reasoning. So making conjectures based on patterns. So you can make them based on observations or on patterns. And then the other term we're going to be looking at is called a counterexample. And that is a specific case for which the conjecture is false. So whenever a conjecture is proven false or shown false, we can see that is a counterexample. So how can we use this in math? So here we need to describe how to sketch the fourth figure in the pattern. Then we're going to sketch the fourth figure. So if we look at our images, our figure 1, we have this circle that's divided into 2, and the top half is shaded. Then if we look at figure 2, it's divided into 4s, and then the left quadrant, upper left quadrant, is shaded. Then if we look at figure 3, it's divided into 6 pieces, and the upper left is shaded. So then we can look at those patterns and decide what this fourth figure needs to look like. So we already talked about, we know figure 1, there are 2 pieces. And figure 2, there are 4 pieces. Figure 3, there are 6 pieces. So there probably should be 8 pieces in the fourth one, right? So that would be our conjecture that there would be 8 pieces. That's part of it anyway. 8 pieces. And then there's also some shading. So in the first one, it was shaded on top. Second one, it's shaded top left. Third one is shaded top left. So by that pattern, we probably need to be shading at least above the halfway line and on the left these 8 pieces. So we also need to shade 1 piece shaded on the left side. So if I draw my 8 pieces, and then I shade above the half line and to the left. So this would be my conjecture, or really my inductive reasoning. It's my conjecture based on the patterns that I saw. So next, it's asking us to describe the pattern and the numbers -7, -21, -63, and -189. And then write the next 3 numbers in that pattern. So we need to look at what is changing whenever we go from -7 to -21? It might be adding, how much you're adding or subtracting. It could be multiplying or dividing. Whatever it is, we have to find that pattern. So looking at -21 or -7 to -21, that's either maybe we're subtracting 14. Well, if we subtract 14 from -21, that doesn't get us to -63. So maybe that's not the pattern. Let's see if we can find something else. We could also multiply -7 by 3 to get -21. Okay? So let's try multiplying -21 by 3. And we'll get -63. So that might be our pattern if we multiply by 3 in this one. So let's try multiplying by 3. So -63 times 3 is going to give us 189, -189. So that looks like what we need to be doing. So we'll take -189 times 3. That will give us -567. Then take -567 times that by 3. That'll give us -1,701. And then -1,701 times 3 will give us -5,103. So using inductive reasoning, I'm guessing that the next 3 in this pattern are -567, -1,701, and -5,103. And we were just multiply by 3 to the previous number. So that would be my explanation or describing the pattern. Multiply by 3 to the previous number. All right, then B, here we need to describe the pattern and the numbers 1, 3, 7, and 13, and write the next 3 numbers in the pattern. So let's look at how it changes from 1 to 3. Well, we could multiply by 3, just like we did in the previous one, but then if we multiply 3 by 3, we get 9. So 9 isn't our next number, isn't 7. So we'll scratch the idea of multiplying by 3 right now. We could also add 2. If we add 2 to 3, we get 5, so that's not quite there. But if we notice, the difference here between 1 and 3 is 2, and the difference between 3 and 4, or 3 and 7 is 4, and the difference between 7 and 13 is 6. Maybe the difference between 13 and the next number is going to be 8. So that looks like a good pattern we can go with. So we would say 13 plus 8, that'll give us 21. And then 21 plus 10, we're still going up by 2, will give us 31. And 31 plus 12 will give us 43. So our next 3 numbers in the pattern should be 21, 31, 43. And that description is the rate of increase is increasing by 2. Rate of increase is increasing by 2. So 2 is that first rate of increase. And then to the next one, that rate increases by 2. And so the new rate is 4, and then that increases by 2, and then it's 6, and that increases by 2. So the rate of increase is increasing by 2. All right, next, we have numbers such as 3, 4, and 5 are called consecutive integers. So any number that is next to another number is consecutive. So 3, 4, and 5 are all consecutive integers. We need to make and test a conjecture about the sum of any 3 consecutive numbers. So we're going to make and test a conjecture. So let's look at 3, 4, and 5. So if we said 3 plus 4 plus 5, well, let's see, that equals 12. So let's think about what we can do, or what we might be able to decide about this. So 3, 4, and 5 equals 12. So we need a conjecture based off the sum of these consecutive numbers. Well, if we look at the middle number 4, 4 times 3 equals 12. So we could say, and that kind of makes sense, if we took 1 away from 5 and put it on the 3, then we would have 3 4s. So maybe that's going to work with any other 3 consecutive numbers, that the middle number can be multiplied by 3. So let's look at that, or the second number, not necessarily the middle number. Well, I guess it would be. So let's try 7, 8, and 9. So 7 plus 8 plus 9, that equals 24. So does 8 times 3 give us 24? Yeah, it does. So we came up with a conjecture based off the observation. We weren't looking for a pattern because it was just a conjecture. And based off the observation, hey, 4 times 3 equals 12. I'm going to make the conjecture that any 3 consecutive numbers added together, that second number will be multiplied by 3 to give you that sum. So then we test it, 7 plus 8 plus 9 equals 24, and it worked out. So the sum of any 3 consecutive integers is 3 times the second number. And that worked out. We could do that with any 3 consecutive numbers, actually. If we tried 10, 11, and 12, added those up, that would be 33. 11 times 3 is 33. 11 was that second number. Okay, looking at number 4, we want to make and test a conjecture about the sign of the product of any 3 negative integers. Sign being, is it positive or negative? So we're going to test a conjecture, make and test a conjecture about whether it's positive or negative with the product of any 3 negative integers. So we're going to be multiplying 3 negative integers together. So if I multiply, so negative 2 times negative 3 times negative 5. So negative 2 times negative 3 gives me positive 6. And positive 6 times negative 5 gives me negative 30. So looking at these 3 negative numbers multiplied together, when multiplied together, I see that I get a negative answer. I'm going to say that the product of any 3 negative integers will be a negative number. So the product of any three negative integers will be a negative number. And we could test that with three more numbers. -1 times -4 times -2. Just keeping the numbers nice and small for mental math. -1 times -4 is going to give you +4. And +4 times -2 is going to give you -8. So our answer stayed negative. So we're able to test that conjecture as well. So the product of any three negative integers will be a negative number, was my conjecture. Then number 5, we want to find a counterexample to disprove this student's conjecture. And they made the conjecture, the sum of two numbers is always greater than the larger number. So maybe they tried doing something like 2 plus 5 equals 7. Well, 7 is larger than the largest number that we added together. So I'm going to say the sum of two numbers is always greater than the larger number. But we want to write a counterexample that would disprove this. So think about it just for a moment. How could we disprove the statement that the sum of two numbers is always greater than the larger number? Hopefully you're thinking of negative numbers. So we could say, well, -6 plus 8 equals 2. Well, the sum is less than the larger number. 8 is the largest number, and 2 is less than that. So we've found a counterexample for that conjecture. So just because we can make some observation that, hey, 7 is greater than 5, I think the sum of any two numbers is always greater than the larger number. It's not always going to be that case. Sometimes you can disprove it. Sometimes you can prove it right. Or sometimes you keep plugging in things that look correct and just haven't come across a counterexample yet. So there was a counterexample for that one. All right, and then the last example. We need to find a counterexample to show that the following conjecture is always false, or the following conjecture is false. So the conjecture is stating that the value, and this is x squared, the value of x squared is always greater than the value of x. The value of x squared is always greater than the value of x. So, well, if we square 2, it's 4. So that value is more than x. So, and if we put in 3, then it's 9. That's still more. So we've got to think differently than those whole numbers. How about fractions? If we use a fraction, and say 1/2 squared. What is 1/2 squared? Well, when you got the square outside the parentheses, everything inside gets squared. So that is, let's do it this way, same as 1 squared over 2 squared. 1 squared is just 1. 2 squared is 4. So here is my counterexample. 1/4 is less than x. X was 1/2. 1/4 is less than 1/2. So we have found a counterexample that shows the conjecture is false. All right, so that was 2.1. Have a great day.